Once just a James Bond fantasy, diamond-based lasers are now becoming a reality. Scientists at the University of Strathclyde are using the unique properties of diamonds to develop a new generation of Raman lasers. Raman lasers work by firing a pump light beam through a crystal, therefore creating heat. And as that heat is generated, the laser beam is converted to a different colour. The materials conventionally used in Raman lasers, such as silicon, are limited in the range of colours they can produce. Diamond, however, has unrivalled thermal conductivity, along with tremendous rigidity, strength and optical properties. So Raman lasers that use diamonds produce light beams with more power and a wider range of colours. Dr. Alan Kemp is a research team leader at the Institute of Photonics at the University of Strathclyde.
Diamond lasers work in the same way as conventional lasers. There are three important components in any laser. We have to have an energy source called a pump to provide energy to a laser material, in this case diamond. That excites the material, and we then use that material as an amplifier for light. And we pass the light beam repeatedly through the amplifying material to generate an oscillating beam, and that's our laser output. So diamond works in the same way as a conventional laser material would. Our interest is that we should be able to make that laser work in more extreme ways by exploiting the extreme properties of diamond.
Martin Dawson is Professor of Photonics at the University of Strathclyde.
In diamond, the process by which amplification is produced is a process called stimulated Raman scattering. And that sounds like a scary thing, but it's basically related to the heating of diamond crystals and lattice vibrations, the shaking of the diamond lattice when heat is generated. Light interacts with diamond, or can interact with diamond, in a very specific way where it essentially scatters from these vibrations in the lattice or produces them. And this process can take place in a stimulated way. The acronym LASER stands for light amplification by stimulated emission of radiation. And this scattering, this Raman scattering process, can be stimulated in a way which allows light signals to be amplified. And that's the basis of any laser.
This research makes use of the very latest advances in the manufacture of high-quality synthetic diamond. And in fact, diamond-based lasers have been around for a while, but this work has led to two major new developments, because they're the first ever tunable diamond Raman lasers, where the colour of light can be adjusted to suit specific needs, and they're the first ever continuously operating lasers of this kind. Regarding the tunable aspect, diamond's optical properties mean that these lasers can produce a range of colours that are much more difficult to generate using conventional methods. For example, yellow-orange light, which can be used in medicine in the treatment of conditions such as vascular lesions or retinal bleeding of blood vessels at the back of the eyes. Dr. Jennifer Hastie is a research team leader at Strathclyde's Institute of Photonics.
All materials have a wavelength-dependent response to light. So, for example, human tissue transmits red wavelengths very well but absorbs blue wavelengths. So if your particular application requires you to look through skin, you need to use red wavelengths to enable optimum light transmission. If, on the other hand, you need the light to be absorbed for example, cauterization of the skin, then you would need to use a wavelength that is strongly absorbed rather than red wavelengths. Red wavelengths in that case would be a poor wavelength to use. So if you have a tunable source, then you're able to tune the laser to the optimum wavelength for your particular application.
Dr. Alan Kemp elaborates on the possible uses of this tunable aspect, such as the ability to produce yellow-orange light.
Why that's interesting to a lot of people, particularly in the medical area, is that blood absorbs, or constituents of blood absorb those wavelength ranges. And if you can tune the wavelength of the output, you can tune exactly which components within the skin, for example, or within the retina are absorbing the light and at what depth, and you can then control the interaction of the laser beam with the retina or with the skin. And that's often used to treat problems with vascular conditions in the skin or with retinal bleeding of blood vessels at the back of the eye, you can cauterise the bleeding at the back of the eye. And by changing the colour, you can change exactly where the beam is absorbed and have much more control over exactly what it is that you're cauterising, and actually damage the right components and not damage the things that you would like to leave behind.
Regarding the continuously operating aspect of these lasers, Alan explains more about the advantages this offers. For instance, in medical treatment for sensitive areas, there are situations where using a pulsed laser would create more acoustic disturbance.
It's not to say that pulsed lasers are not important, of course they are, but continuously operating lasers can do some things that pulsed lasers can't. And one example of that is when medics wish to treat the retina, for example, and it turns out that pulsed lasers are just too damaging to the retina. They tend to cause too much collateral damage around the retina, so that the medics would prefer to work with continuously operating light sources where they can specifically target, deliberately make damage, or cauterise blood vessels, for example, very locally without doing damage to surrounding tissue.
One of the real attractions of this technology is that it could be used as an add-on to other lasers, as a way of making other laser systems more versatile. This world-leading research is funded by the Engineering and Physical Sciences Research Council. In the long term, a wide variety of areas could benefit, ranging from pollution monitoring to the treatment of diabetes-related eye conditions and cancerous tumours.